Hello everyone. So let's revisit some of the concepts and things that we already have learned. So first, the merge sort. If you remember when you did a merge sort, we did suppose merge sort on an input A. We divided it into two parts, first part and the second part. And then we said like we recursively sorted the first part and the second part, right? So what does it mean? So it means that we actually did the same thing on these two smaller portions. We divided into the two and then kept on doing this, right? So you already know about this. If I look at the pseudocode for merge sort, so this was the pseudocode for merge sort. Our initial input was the input array A, where we had the left index and the right index. And then we found the middle index, right? That's how we divide this array into two. And then we call the merge sort again. So this is recursively calling. You see, we call these merge sorts inside a merge sort, right? So what actually it does, so we call it the recursive calls. And these smaller merge sorts actually happen on smaller arrays. So this one takes only from the left index up to the middle index, and the second merge sort happens from the middle plus one index up to the right index, right? So basically we are calling merge sort again inside a merge sort. So that's first thing. That is a recursion. So the next thing we saw was in quicksort. So we're given an array, input array S, and we called quicksort on this input array. The way we did it is we selected a pivot. That was the first part. And then we partitioned the set S into two, S1 and S2, right? And then what we did was we called quicksort on both of these. So we called quicksort on this, we called quicksort on this, right? So that means inside quicksort of S, we call quicksort of S1 and quicksort of S2. So if I look at the code, this is what we did. We called quicksort and say input array is A, and then from the left index up to the right index, and then we found the partition index. This is the index of the pivot, right? So we call the partition. So this was the index of the pivot that we selected, and then we called the quicksort twice. First from the left up to the partition index, less than partition index, and then from starting from right after the partition index, right after the exact position of the pivot up to the right. So you see, we call this quicksort recursively inside another quicksort. So that is another recursion. So let's talk about what recursion is. Remember, recursion is not an algorithm or it's not an abstract data structure. Rather, it's just a technique to design algorithms. Okay. So we know that sometimes the best way to solve a problem is by solving the smaller version of the same exact problem. For example, if someone asks you that what is the best way to go from, say, Dallas to, someone asks you what is the best way to visit like travel between Dallas to San Antonio. Okay. Now you know that you have to go to San Antonio through Austin, right? So you can break this problem down, and then if you can find this smaller sub-problem, you can ask this question: what is the most optimized way to travel between Dallas to Austin? And then you again ask the question: what is the optimized way to travel from Austin to San Antonio? And then you can combine them and get your whole solution, right? Okay, so recursion is a technique. It's a technique that solves the problem by solving a smaller problem of the same type. So you break down your problem into smaller ones and then solve the exact same problem on the smaller set and combine them and then get the result for the bigger one. So let's talk about a real life exercise or example. Suppose uh, students have formed a queue or a line or a column in the classroom. They have formed a column. Now, someone in the front, he wants to know. Uh, let's say it's not in the classroom, in an open space or something. A group of students have formed a column or queue. So someone in the front wants to know that how many students are standing in the column, but he cannot move from there. Just think about this. He cannot move. He can just, and also he doesn't have such powerful vision to look all the way behind and count. So what he can do is, now he has a problem. He wants to uh, know that how many students are actually standing in the queue. So what he can do is he can ask the person next to him. So there is a person here, right? Standing here. There's a person here. He can just ask him or her, right? So suppose this was the person in the front. He can ask the person behind him, hey, do you know how many uh, people are standing in the queue? Now this person also has the same problem. You see, she also doesn't know how many are behind her. She asks the next person behind her, right? So he keeps on going and going. Okay. Now two things. You see that everyone is actually, this person has the problem. His problem is the length of the, say, length of the queue, right? He had this problem. Now he passed this problem to the next person. Next person now again has the same problem, like length of the queue. You keep on passing the same problem, but the problem becomes smaller. You see that? So this is a larger problem. And as you send it behind, it becomes like smaller. So you can think it as a real life recursive call. Okay. So you call the, like, you made a recursive call. Now how do you get your result? The result you get is, if this person finally tells you that, hey, there are like in -1 people behind me, then what you can do is you can use this result and add yourself, the n-1 plus n-1 plus 1. Okay, so this is the final result. Similarly, this person actually got this result n-2. This person told this, suppose it said, or let's leave n. If it, so someone said like, hey, there were like 52 people behind me, so I can get this result and add 1 and say, oh, okay, there are 53 people including me in the line. Okay, so one important thing is, from once you do the recursive call and once you get the result from the smaller problems, you have to know a way to combine the result from the smaller problem to get the result for the larger problem. Okay, that's one thing. And the second thing is, this recursion call cannot go on forever, right? Can I just keep on asking like forever? Actually, there is someone who doesn't have any person behind him or her, right? So that person, suppose, is here. That person says, oh, okay, you see, there is 0 people behind me. That is called the base case. So any recursion should have this base case. Okay, so this is a base case. So any recursive algorithm should have this base case where at least one person start saying, oh, I know the answer, and then he passes the answer to someone else. He now recreates his own answer. Okay, so there must be a base case where the recursion stops. Okay. Okay, so every recursive algorithm involves at least 2 cases. One is the base case. A base case means a simple occurrence that can be answered directly, right? Because the last person, he didn't need to ask someone else. He knows the answer. Oh, there is nobody behind me. Okay, so this is a simple occurrence that can be answered directly without asking anyone. And the recursive case, which is the complex occurrence of the problem that cannot be answered directly, right? So these calls were like recursive. When I asked her, hey, how many people are behind us? She doesn't know the answer. She had to ask someone else, right? And this person also had to ask someone else. So these calls are the recursive calls. And this person is the base case. Once he asked him, he doesn't need to ask anyone, he knows the answer. Okay. Okay, some recursive algorithms can have more than one base case or recursive case. We will show them. But all algorithms have at least one base case. That's the crucial part. So in the crucial part of recursive programming is identifying those cases. So let's look at the base cases where our recursion will stop. So in case of quicksort, the base case was when the left index is greater than or equals to the right index. That means we have one or zero element left. And if you remember, like if we have just one element left, it's already sorted, right? So if you call a quicksort on an index where left is smaller, greater than or equals to right, what does it mean? If left is equals to right, that means there is one element, right? That means one element. So one element is already sorted, so we just return it, done. If left is greater than right, that means there is no element left, zero element. That means we don't have anything to sort, we are done. So that is the base case for quicksort. Now let's look at the base case for merge sort. For merge sort, we're given an input array and then the left index and the right index. And the base case is if at some point left index is greater than equals to right index, then return. Just similarly, this means that if the left index is greater than the right index, that means there is no element left. So we are done, zero element. We don't need to go any deeper. If the left index is equals to the right index, that means one element is left, and that is where we stop. We know that one element is already sorted, right? Okay. Okay, so let's talk about an algorithm that can be solved recursively. So n factorial. I think all of you, since you're in computer science, or even if you're not, you know what n factorial is, right? So n factorial is n into n minus 1 into n minus 2, right? Up to 1, right? This is the n factorial. Now, can we say that n factorial can be written as, what is this part? Can I say that this is n minus 1 factorial, right? Can I say that n factorial is actually n into n minus 1 factorial? Now, can we say that we actually have a larger problem, and then we are solving it using a smaller problem of the same problem of a smaller size. So if I know n minus 1 factorial, I can calculate n factorial. I can further break it down, like n minus 1 factorial can be solved by n minus 1 into n minus 2 factorial, right? Okay, so that means I have been able to create a recursive case. So to turn it into a recursive algorithm, we need a base case, right? What is the base case? So the base case is 0 factorial. Okay, so once it reaches 0, then the value becomes 1. And we can write 1 factorial as, so 1 factorial is 1 into n minus 1 factorial, that is 0 factorial. Okay, that is 1 into 1. 1 factorial is also 1. Okay, so we can define it now that n factorial is 1. That is the base case. And this is a closed form definition. We can just make it recursive. like this. So this is the recursive solution for this, okay? So we write this portion as n minus 1 factorial into n. Okay, so let's talk about another recursive problem. This is called as Fibonacci number, or some call it Fibonacci. Yes, whatever it is. So the base case for this problem is, we know the 0th Fibonacci number is 0, and first Fibonacci number is 1, okay? So the second Fibonacci number is the sum of these two, the previous two. So the second Fibonacci number is 2. The third one is the sum of the previous two, which is 2 plus 1, 3. Next one is 3 plus 2, 5. Next one is 5 plus 3, 8. Next one is 8 plus 5, 13. Okay. Next one is 13 plus 8, 21. Okay, so you see this can be defined recursively. So the 0th Fibonacci or Fibonacci number is 0. First Fibonacci number is 1. So we can define any, say, nth Fibonacci number as the summation of the n minus 1th Fibonacci number plus n minus 2th Fibonacci number if n is greater than equals to 2. So we take the summation of the previous two Fibonacci numbers to get the current Fibonacci number. And this is the recursive case. And this is the base case. We have two base cases here. Okay, so if I draw it like draw the function calls like a tree, it will look like this. So for Fibonacci number of n, it will make two calls, Fibonacci of n minus 1 and Fibonacci of n minus 2. It will make these two calls, okay? And then it will add them up. Okay, so you see that Fibonacci of n breaks down into two smaller problems, right? Similarly, Fibonacci of n minus 1 again breaks down into two smaller portions or two smaller calls, right? It will call Fibonacci of n minus 2 and Fibonacci of n minus 3, and then it will add them up. Similarly, this one will also break down into two. So it will keep on going until we reach, say, f of 1 or f of 0. So until we reach there, it will keep on going